morning everyone. Today we are going to see operating system unit 4 session 2. In the previous session we have studied what is memory management, address banding. Under that we have seen compile time, load time, execution time and address translation from logical address to physical address. In today's session we are going to study swapping. So swapping technique is used in operating system when you are bringing the process from secondary memory to main memory, and as you all know that main memory is a limited memory, and if the main memory is full, if there is no space for a new process, then in such situation the process which is very old or the low priority process, so old process or low priority process will be swapped out, that is will be removed out from the main memory and will be sent to the secondary memory, and the process which is a new will be swapped in the main memory in place of that process. So the process which is very old and low priority process, such processes will be swapped out from the main memory and will be sent to the second memory, and in exchange with that a new process will be swapped in the main memory for execution. You can see this swapping technique in below diagram. So this is a main memory and this is a secondary memory. So the process will be swapped out, the old processes, low priority processes will be swapped out and the new process will be swapped in, and the old process which was swapped out, it will keep all its information in a PCB. PCB is nothing but process control block where all information about that process you will get. So currently where that process has stopped the execution, currently which line, and then again it is loaded into the main memory when there is a space in the main memory, or that high priority process when it has finished its execution, then it will be brought back to the main memory for remaining continuation of the processes, remaining execution of the processes. Then that information will be fetched out from this PCB, currently where it has stopped and how much part it has to execute, and then it will resume its execution. So this is swapping technique used. Definition: a process can be swapped temporarily out of memory to a backing store and then brought back into memory for continued execution. This backing store is nothing but our secondary memory where it will store a large amount of data. Rollout, swap in and swap out, you can also call as rollout and roll in. Next we'll see memory allocation. So operating system has two responsibilities: space memory allocation and address translation. Address translation we already seen how it translates from logical address to the physical address. Now in this space memory allocation there are two types: contiguous memory allocation and non-contiguous memory allocation. Contiguous memory allocation means bringing process from secondary memory to main memory and allocate all process data at one particular location. Next is non-contiguous memory allocation, bringing process from secondary memory to main memory and allocate the process data into different locations by breaking the data into different blocks. So let us understand the difference between contiguous and non-contiguous memory allocation. Now suppose there is a secondary memory and a main memory. So you are going to bring the processes from secondary memory to main memory for execution. So now the memory will be divided into the number of blocks, whether it is a secondary memory or main memory. So the memory like this way, it is divided into blocks. And same way in the main memory also you can find out different blocks here of memories. So in these blocks your data will be stored in the secondary disk. The data can be anything, it can be file or any other files. So whenever you are going to bring the processes from secondary memory to main memory, then suppose you want to bring this data to the main memory for execution, then it is treated as a process. So in the main memory, at which location of the main memory you are going to bring that process, where that process will be stored and will be executed. So in a contiguous memory allocation, the process which you are going to bring from secondary to main memory, all process will be located at one place. Means all data of that process will be placed at one location. That means the process will be not breaked. So data will be in a contiguous form. Now suppose there is another process which you have brought from secondary memory to main memory, and this process can occupy 1 block, 2 block or 3 block. So all this data of that process P2 will be stored in contiguous form, one after the other. Whereas in a non-contiguous, what happens? When you bring the processes from secondary memory to main memory, the data can be located at, that process can be stored at any place. Means wherever there is a space available in the main memory, there that process will be stored. Now suppose this block is free, then that process will be stored in this block and remaining other blocks are occupied. Then suppose here is a free block, then some data of that process will be stored in this location and some of other data of that process will be stored in some other location. So in a non-contiguous, the process will be breaked and will be stored in different locations. Whereas in a contiguous location, all data of the process are stored in one location, no breaking of processes. So there must be space in the main memory where that process can fit at one place in a contiguous memory allocation. And whereas in non-contiguous allocation, wherever the space is available in memory, there that process will be breaked and will be stored in different location. So this is the difference between contiguous memory allocation and non-contiguous memory allocation. So contiguous memory allocation. Single contiguous allocation is a simple memory management scheme that requires no special hardware support features. So this technique, contiguous, non-contiguous, this is implemented inside the operating system. In every operating system, you can find out no external devices are to be connected or drives are needed. For allocating memory, it is divided into number of fixed size partitions. So as I told you, the memory of secondary memory or the primary memory, main memory, it is divided into fixed size. You can see here. That is, this is the main memory and there are fixed size of blocks. So whatever the size is given for these blocks, it is of fixed size. Now suppose this block is given 2 MB and for this block is given 5 MB. So some of the blocks of the main memory are of fixed size like 2 MB and some of the blocks you can find of different sizes like 5 MB, 3 MB, 4 MB. So you can find out, but these are fixed. So that memory block is of fixed size. It will not change. So if the process fits within that block, then it is going to fit. Otherwise, it is going to use remaining blocks also. And here, each partition contains exactly one process. See, each block contains only one process. So in each block, in each partition, you can store only one process. No two processes are there in each block or partitions. So now suppose this process is using these two blocks. So some of the data of this process is in this block and another data is in this block. So these two blocks are occupied by that process, and if there is a remaining memory is there, then it is just a wastage. That memory cannot be allocated to any other process. Degree of multiprogramming depends on the number of partitions. That means as we have main memories of limited size, so how many processes has to be brought from secondary memory to main memory will be decided. Now suppose if you want to bring 10 processes in the main memory, but as main memory is limited, instead of bringing the 10 processes, the operating system can bring the 5 processes in the main memory by looking at the how much memory is available in the main memory. If partition is free, process is selected from the input queue and is loaded into the free partition of memory. If these blocks are free, then processes are selected from secondary memory and will be loaded into the main memory for execution in those free partitions. In a contiguous memory, there are again two types: fixed size partition and variable size partition. Fixed size partition means, you can see in this diagram, process 1 and process 2 has used all the memory of the block, and whereas process 3 has not used all the memory of the block, still there is a memory and which is just wasted, because one partition, one block, only one process. So remaining the memory which is available in that block, it is just wastage. And in this diagram you can see process 4 has occupied these 4 blocks. So all the 4 blocks belongs to process 4, and this remaining memory which is available in different partitions, this is just wastage. So this is what fixed sized partition, where you cannot change the size of the partitions, and one block, one process. So because of this, it faces the internal fragmentation problem. These blocks are of fixed size like 2 MB. Then all blocks, most of the blocks you can find out fixed size like 2 MB, like this way. And you can also find these partitions of unequal size, means some of the blocks are of 5 MB, some of the blocks are of 4 MB, some of the blocks are of 3 MB. Unequal size, but these blocks are fixed. You cannot change it. So main memory is divided into number of fixed partitions at system generation time. A process may be loaded into equal partitions. It can be equal or greater partition. So memory manager will allocate a region to a process that best fits in. So the memory manager is there in the operating system. So it will decide in which partition to allocate the processes. So unused memory within an allocated partition is called internal fragmentation. Now suppose one process has come with 2 MB. So one process needs 2 MB and all other blocks are occupied. These blocks are already occupied. Now this block is free. Now here that process needs 2 MB and this block is of 3 MB. So the process, you can allocate this process, this block for process with 2 MB. So when 2 MB is occupied, 1 MB will be free from this block. So 2 MB is occupied and 1 MB is still remaining here. And you cannot occupy that to any other process, as there is each partition can hold only one process. So because of this, the other remaining memory, that is 1 MB memory, will be wastage here. You cannot allocate it to any other process, as it is a fixed size partition and one partition, only one process. So because of this, you cannot allocate the remaining memory to any other process, and that problem we call it as internal fragmentation. The wastage of memory after allocation of the memory. You can see in this diagram, fixed size partition can be of equal or unequal sizes. These are equal sizes partition and these are unequal size partition which are fixed in the main memory. When the process terminates, the memory partition becomes available for another process. So whenever the process finishes its execution in the main memory, then that partition can be given to any other process. So as we already discussed internal fragmentation, then that is allocated memory may be slightly larger than requested memory. This size difference is memory internal to a partition but not being used. So the remaining memory cannot be allocated to another process. It is just a wastage of memory. Whereas what is the external fragmentation? Gaps between allocated contiguous memory. Total memory space exists to satisfy a request, but it is not in a contiguous. So you can see in this diagram, this is the fixed size partitions of unequal sizes. And after allocation of the processes to the main memory, in this diagram you can see these are the remaining memory spaces available in that partitions. So you can see here 13 MB was available, and after allocation only 2 MB is free now here. So here under different partition there are memory available, free space memory available. But this memory is not in a contiguous manner. It is not at a one place. So at this partition you cannot allocate some new processes. That is one partition, only one process. So these all are like wastages. Now suppose one process comes with 4 MB. One process comes with 4 MB. That process name is, you can take P5 process. The process P5 comes with 4 MB. Now you can see in this memory, how much memory is available here. This is 2 MB, this is 2 MB, that is 4 MB, 5 MB and 6 MB. 6 MB memory is available in the main memory. And the new process has come with the request 4 MB. See, the memory is still available in the main memory, but it is not in a contiguous form. You cannot find out this all memory at one place. So because of this, you cannot allocate the process P5. And this problem we call it as external fragmentation. Memory is available in the main memory, but because it is not in a contiguous form, you cannot allocate the process. So this problem we called as external fragmentation. But there is a solution for this external fragmentation, that is compaction. So compaction is a technique. So in this, what you are going to do, the memory which is available in each partition, this all memory you are going to bring at one side, at one end of the side. You are going to bring it so that all memory will be allocated to one place, will be gathered to one place. Now you can allocate the process to, now you can allocate the memory to such processes, because all memory is at one end or at one place. So like this way, using the compaction technique, we can solve the problem of external fragmentation. Next is variable size partitioning. So in a variable size, there are no partitions. How the process comes, based on their size, memory will be allocated, and remaining memory can be used for other processes. As in this technique, there are no partitions. So how the processes come, that way the processes will be allocated in the main memory. Now suppose this is a main memory. As there is no partitions, so how the processes come, that way the processes will be allocated to the memory. In today's session, we have seen memory allocation and what is the difference between contiguous and non-contiguous memory allocation. Thank you.